when I started to think about what to talk about today, a presentation Czech gave about 3-4 years ago came to mind. And of course, you all have seen the picture and the LINPACK guide picture before I come to that. But what intrigued me about that presentation in particular was the title, The Confessions of the Accidental Benchmarker. And I was curious about what he actually meant by accidental, if it was as obvious as it seems to be, or if there was something more behind it. So I started thinking about it. And of course, the reason he gave was that Appendix B in the original LINPACK report, or more precisely in his private copy of the LINPACK report, because I don't think that column in the table exists in any other copy, unless I'm mistaken. It was really a photocopy, where he for the first time actually calculated performance values for the LINPACK problem. So was that an accident? I think as I'm going to argue, it doesn't look like an accident to me. Maybe the column itself was an afterthought, but if that was an accident, it was a heck of an accident. So in 1993, when I came into the picture, we started the TOP500 project. That was 16 years after the LINPACK report came out, and Czech calculated his first column. And when we started the TOP500 project, which is intended to produce a table of the largest supercomputers twice a year to produce market statistics, when we did that, we looked for a good measure, a good yardstick for what a supercomputer is and how we could rank those systems. We looked around, we came up with a couple of criteria, which you can see on the slide. And the most important observation we had at that point was simply the last point, was that the LINPACK benchmark at that point already, the HPL LINPACK benchmark. So Czech had already gone from 100 by 100 to 1000 by 1000 to arbitrary problem size at that point. That particular benchmark had by a large margin the largest coverage of any for systems on the large diversity of systems for which Czech listed numbers. So it was pretty much a no-brainer in 1993 to use the LINPACK benchmark as a yardstick for the TOP500. And we asked Czech to join forces, not just because of the LINPACK, but we wanted to collaborate with Czech in general. And the success we had with that choice, in particular with the LINPACK benchmark, was much higher than we actually thought. We could do a lot more things than we thought, and it lasted a lot longer than we actually thought. This is one of our signature slides, where you see in orange the performance of the last, the number 500 system on the list, the performance of the first system on the list, and in blue the sum of all 500, which I think of mostly as 500 times the average system on the list. And the astounding fact here is, if you look at the history of the 28 years of the TOP500, that we were able to actually hold on to LINPACK benchmark, to the HPL, and that we were able to use the HPL benchmark across all these systems. Because if you look in the lower left corner, the last system on the first list had 422 megaflops performance. And on the top right corner, the red data point, that's the Fugaku system, that's the current leader on the list, has 442 petaflops. That's of course a factor of 10 to the 9 in terms of performance. And nobody can expect that a piece of code holds up across that range of performance and across that range of time. But HPL did actually very well, and it still serves its purpose in some sense very well for us in the TOP500. So why did LINPACK do so well? I tried to really boil it down to the two most essential causes I see in the framework of the TOP500, why it did so well. The first one is really a benchmark which you want to use across a large variety of systems, has to have a scalable problem size, and LINPACK is really the prime example for having a problem which is easy to scale and continuously to scale. That makes comparisons across different machines and different sizes a lot easier. Overall, it's comparably simple to some of the other benchmark, but it's not overly simple. It still solves an actual problem, is an important routine by itself. The second reason, that one really came out and was very important at the beginning, but really proved itself over the first couple of years of the list is that the LINPACK has that unusual feature that you get the best LINPACK performance on any system if you use all the memory and if you use the full system. That's not a given. If you just start out with any mathematical problem and code it up, typically what happens is you end up with a formulation that has highest performance values if you if you run out of a lower level of the memory hierarchy, such as the caches. And performance, in-cache performance is not what we were looking for, is not what's really a characteristic for a large-scale use for HPC systems. So HPL having that feature that it's best to use the whole system, the whole memory, that is really a self-correcting feature, which brings out in the long run the correct trends and avoids a lot of rules and a lot of head scratching afterwards. That's the more important features. Of course, over the years we had also because LINPACK, when you increase problem size with modern formulations, its computational intensity measured in terms of floats per bytes increases tremendously. Because of that, over the year, we got more and more criticism, and the people with their shiny new machines, they came and said, we don't really like the LINPACK benchmark because everybody can do so well on the LINPACK benchmark. We can't really show off what our machine can really do on real applications. So over the years, we had many attempts ourselves and other people to come up with new benchmarks. And I tried to summarize just the most important features we were looking for in new benchmarks to augment the HPL benchmark. The most important one, of course, for us was not to do the one shortcoming, not to replicate the one shortcoming LINPACK has, that its arithmetic intensity changes with the problem size. So ideally, we would like something where the float to byte ratio in the algorithm is on the order of 1. It doesn't change with problem size. So we get more of an apples to apples comparison between vastly different machines. A secondary reason was that we also wanted something which where the features, especially the execution times, I would just scale with the size, maybe with the size of the system, and not go up overly go up with problem sizes. So there have been numerous attempts. Czech did a couple of them himself. And Piotr already talked about one of the more recent ones, which seemed to have the most traction of that. That's of course, the HPCG benchmark, the high performance congruent gradient benchmark. Happens to be another numerical linear algebra code. And it does actually fulfill all the criteria, not just having the benefits of the original HPL in terms of problem size and so on, but also having that added benefit that it actually is very sensitive to the arithmetic intensity. Here you see an analysis I did like 3 years ago when we had enough HPCG numbers, where I plot the efficiency relative to the peak performance of a machine on the vertical axis over the byte to float ratio of the underlying hardware of the architecture. And you see systems which have a higher memory bandwidth relative to their floating point performance tend to have higher efficiency on the HPCG benchmark. So HPCG is certainly very sensitive to main memory bandwidth and probably also to other things, and adds additional dimensions. So we were quite happy with that because it's a real good complement to HPL in that respect. Of course, immediately or very shortly afterwards, the same people with their shiny machines came and said, we don't really like HPCG either because HPCG is such a hard benchmark that we on our machine cannot make it look good. So we don't like that either. So we had two benchmarks we were criticized for. And then Mike and Piotr and Czech, of course, explained that very well in terms of the bookmark analogy, that HPL is the higher end of the performance range and HPCG is supposedly the lower end of the performance range, and the real performance is somewhere in between. I thought of it more of as an iteration. The first iteration was the result was too high. Then the compensation, the second iteration, the results were too low in HPCG, and I expected Czech to come up with a benchmark somewhere in the middle where people finally would be happy. Of course, Czech did not do any such thing. The next main benchmark he came up with, he named HPL-AI. Now, the first thing you have to notice about HPL-AI is Of course, AI is in the name, but that only refers to using reduced precision in its calculation. There's actually nothing to do with neural networks or deep learning or anything like that. Nevertheless, it's very clever to name it that way. And what it does, it uses the original HPL problem. There's nothing new there. It's HPL, but it does it in a reduced precision format, which requires changes to the algorithm with an iterative refinement to achieve the full precision of the solution and those things. And to measure that, he said we measure it on the same scale as HPL. We basically take the number of floating point operations traditional HPL would have to perform and divide it by the time the HPL-AI, the mixed precision benchmark needs. In doing so, we get a number which we can compare to HPL, and we really see the benefit of the reduced precision calculation, which you see here in the second to last column. That's the HPL-AI count, which is equivalent HPL floating point operations per second. And you see that number one system right now, the Fugaku in Japan, actually has an equivalent performance of about 2 exaflops. So instead of producing a benchmark which would be somewhere in the middle between HPL and HPCG, Jack came up with a benchmark to produce even higher performance numbers than HPL, but for a good reason, because he wanted to show the benefits of mixed precision arithmetic. I don't know if Jack has heard from the people with the shiny machines, but at least I have not heard complaints about it. Maybe it's not on their radar screen yet. It's still a new benchmark, but that's to be seen. So with that, I like actually to talk a little bit about the top 500 itself. Of course, I already showed you that slide, and here in the faint dotted lines, you see actually the exponential growth curves and extrapolations. And one of the observations we have talked about in the past quite a bit is that we see inflection points, or we saw inflection points in the curves for the entry system and for the average system or the sum. And the thing which really caused us quite a bit of a headache to explain initially was why those two inflection points on those two levels of the list, the entry and the average, why those two inflection points were 5 years apart. So the entry level was the first one where we saw a slowdown in how fast performance increased in the list. It was in June 2008. And around that time, of course, the big topic, one of the big topics was the end of the NAR scaling in our chip technology. So we attribute that inflection point to the end of the NAR scaling and to the chips with a less and less increase in cycle time showing up and taking over the system. The delay for 5 years, that was a little harder to explain, but we got some hints. One of the most important one is shown on this slide, where you see the average age of a system in the top 500. So the top 500 has this list of 500 systems, and we just calculate how long has that system been in existence or been in the list. And you see around 2008, the age of our systems started growing quite substantially. It used to be very dynamic. The turnover in the list has slowed down quite a bit. The systems in the list are much older than they used to be. That effect, if I separate out research and commercial markets, is actually more pronounced in the research market than in the commercial market. And the question is, what's causing that? What's going on there? My interpretation for that is simply that with the end of the NAR scaling, when we were according to the old procurement cycles and timeframes, when we looked at new machines, we found that they didn't provide enough delta increase in performance, and we delayed our procurement cycles. So we increased time for our procurement cycles until we could buy a machine which was sufficiently faster than the old system. And for that led to an aging of the population in the top 500. We also had a second effect for centers which had an annual budget which was independent of their procurement cycle. They could actually save the money by extending their procurement cycle, and once they bought a new system, spent more money on the new systems. So there was a physical increase in the system sizes during that time, which in turn basically delayed the impact of the NAR scaling at the high end, because we compensated for the lack of chip performance by increasing the number of processors and the number of nodes over proportional. That is a thing which only happens basically once, and at some point we find a new average. People settled on a new procurement cycle, which was slower than before, but the growth rate basically changed quite suddenly in the top 500 overall. Here you see in blue the actual annual performance increase of the top 500, and in orange you see the two averages up to 2013 and since 2013, and the averages are quite different and match the blue curves actually reasonably well. So the old performance growth we had in the list was higher than Moore's law, and it meant it implied a factor of 1,000 performance increase within 11 years. We saw that up to about 2008-2013 timeframe. Moore's law would have been a factor of 1,000 in 15 years. So we had a nice, we were nicely above Moore's law due to increasing system sizes even before the NAR scaling ended. But after the NAR scaling ended, and after we didn't want to increase our systems more or delay our procurements more, we settled on a new growth rate, which now implies a factor of 1,000 in 20 years. So it takes us basically twice as long to achieve or to see the same increase in performance, in peak performance, HPL performance in the market than it did before. And with that, of course, there's all kind of changes coming into the market as well. So the delay between 2008 and 2013, that was really that increase in procurement cycles, the aging of the systems and things like that. The interesting question now for me was, and I looked into that in more detail 2 weeks ago when we published the last list, was what's actually going on at the very end of the list, just the last couple of, oops. I hope you're still there. My computer just went to sleep. So what I wanted to look into more detail is really what's been going on the last couple of years, what happened at the right end of the list at the last couple of editions. And for that, I'm going to just take the data points after that second inflection point in June 2013 and just focus on those. And to get a clear signal, I had to do one more thing. So this are really the trends for the top 500 overall. But the top 500 is really a mixture of two very different populations, two very different markets. One is the market for real high performance computing in the traditional sense of engineering. Those are mostly systems at research centers or at universities. And that population tends to have a different behavior compared to the commercial market, which is driven by a lot of databases, warehousing, and other operations which are not necessarily typical for HPC, at least not 30 years ago. So I took those two markets apart, and to avoid any bias in my sampling, I cut both of those populations short to 100 systems. So the next slide is a slide where I show you curves for the top 100 research systems and the top 100 commercial systems. And if you do that and we compare it to the top 500, it becomes kind of evident that there is actually or has been another inflection point in our growth rates, especially for the research systems, which happened about 4.5 years ago, 9 lists ago. Up to that point, we grew on that rate of 20, a factor of 1,000 in 20 years. And since then, at the end of the list, this is the size of the last of those 100 research systems. The end of that list grows at a lower rate and seems to be stable growingly at a lower rate. We do not see any such effect for average system sizes yet. So there is seems to be something similar going on as we had seen with the end of the NAR scaling. The red curve for 2 years seemed to power ahead on the old growth curve, but now has retreated back. And if you just connect the data point 9 lists ago and the current data point, you pretty much get the same growth rate as for the research systems. And that is an important observation that even though it didn't look like it at the beginning of this trend, nowadays I would argue that the commercial market actually shows the same slowdown for the last system as the orange line. The bump in the middle on the commercial line, that was probably some side effects, some secondary effects due to weird behavior of Chinese manufacturers as well as Chinese customers. There was a flood of Chinese systems, which has gone away, has ebbed away. So I argue that the red curve follows the same line as the orange curve. That's important for the interpretation. So 4.5 years ago, several things happened. There was a change in US administration, and a lot of exascale computing projects were kicked off that might change availability of funds or might change allocation of funds. But now, because I'm convinced, I now argue that the commercial market behaves the same way. I would actually argue that it is a technological factor which drives that inflection point. And of course, the last couple of years, we have been talking very much about the end of Moore's law and its impact on chip technology. And I think what we are really seeing is the first hit of the end of Moore's law, where chip technology and chip speeds of our chips, performance of our chips, doesn't grow as fast as previously. It shows up just like the end of the NAR scaling at the entry level of the top 500 first, or top hundreds in this case. And the question is going to be, how long is it going to take to propagate through the list till growth of performance on all levels slows down to this new level? And if it's the only hit we're going to see, or if that's going to be a frequent occurrence now as we go through the different stages of the end of Moore's law. Because I don't think end of Moore's law is really a singular point. I think it's really a couple of events gonna take place over 10 or 20 years. So with that, I try to do something which is close to a summary of what I just said. Of course, coming back to the title of the talk, HPL certainly wasn't accident. The column might have been an afterthought. But if that was an accident, there was a hell of an accident, and it lasted like over 40 years, 45 years with tremendous success. So I would like to have some accidents like that, if that's what it takes. Well, of course, if you read the title properly, Jack didn't say that HPL was an accident or the benchmark was an accident, but the benchmarking or the benchmarker was an accident, the accidental benchmarker. And I think that speaks much more to what I realized, that Jack's first scientific love seemed to have been numerical linear algebra, and he's probably still true to that love. And that makes the side activity of benchmarking the accident. That I could see. However, doing so, he's actually really successful. And I'm curious if there is a hidden agenda, because the most successful benchmarks over the years, and Jack did many benchmarks, Piotr mentioned some, there was also others like Parkbench and so on and so forth. Some of us were involved. The most successful ones seem to be the ones which are just algorithms from the numerical linear algebra topic. So in some ways, I think he's out to proving that linear algebra is really everything you need to measure HPC performance. So he's making good progress on that. Of course, take that with a grain of salt. And overall, from the point of view of the top 500, I have to say HPL served us tremendously well. The top 500 wouldn't be able to have done anything close to this without a benchmark like HPL. It still does serve us very well. That's quite amazing, considering the range of performance and the range of time. And I'm looking forward to what we see in the future, and continue to produce the list together with Jack and analyze it twice a year at least. Thank you very much.